So now I kind of want to get into free body diagrams. Now we get into free body diagrams. Or you know what? I'm gonna like make free body diagrams the first step in how to solve force problems. And the reason being, you can talk about free body diagrams all you want. You're only going to get value out of it if you're actually making them. So how to solve force problems? Like this is literally like if you just follow like these 3 steps. Like no one like tells you this. I wish they would, but it's like 3 steps every time. It's draw the free body diagram. Step 2 is write the sum of forces, aka Newton's second law equation for the x and or y axis. Like that's literally what you should be doing. You should be making it for the x or the y axis, like whatever you need, and then write the sum of forces, Newton's second law equation, x and or y axis, and then you get into step 3, which is solve for whatever. And whatever can be acceleration, it can be a distance, it can be a time, it can be a final velocity, it can be an initial velocity. It can be like so much, like you don't understand like solving for it. Like once you have the free body diagram and you use that to make the sum of forces equation, like literally the problem is like 90% done and you just have to do the algebra left. And the problem is that most kids just have trouble getting like the first 2 steps down. Like the free body diagram and the sum of forces equation is like the hardest part for a lot of people. And like I understand why, I get it. Because it's not like easy and that straightforward. Like there's different like every problem has its own context, right? Like if you're pulling a crate, that's gonna be different than if you're like stopping a car. It's gonna be different if you're like pushing an object down a hill. It's gonna be different if you're using like a pulley system to like raise something or lower something. Like there's so many different contexts to the problem that like these 3 steps, although they're the same every time, they follow like a different methodology every time. It's like, I get why it's hard, but it's not that hard once you actually start doing it. Here's an example. If I have a box here and I'm pulling on that box with a force F like this, and the first thing we would actually have to do, this is like a step 0. Like I'm going to include a step 0. Split components. And that's like a necessary step because if we have a force F here pulling this box, then we don't have a choice, and there's like some angle theta here. We need to split this up into the x and the y component. Like we can't ignore that. That problem's not going away anytime soon. And so if we draw the other forces, gravity always points down. It's on Earth. Gravity points down. And then we're also going to have a normal force. And the normal force is there, again, because the surface is perpendicular to the surface. The normal force is keeping the object up. That's just what it is. So then we have Fx. Fx, if you remember from geometry, is going to be F times cosine of theta. And cosine because it's the adjacent leg to the angle. And like in general, if you don't even know where the cosine's coming from, it's like cosine of theta is equal to the adjacent leg over the hypotenuse. And the adjacent leg is Fx. The hypotenuse is F. And then if we were to do the same thing for sine of theta is the y component divided by f. And it's the same reason we can like redraw fy on the right here to complete like a right triangle like this. Most people have trouble with that too. It's really unfortunate. I just don't know why. It's just as easy as moving the thing over, that vector over. And now we have cosine theta, we have sine theta, we have like everything we need. And then we would just plug in like the sum of forces equation. I'm not going to do that right now, but like that's what you would do.